In this video on inner products, we have three objectives. We're going to define and compute inner products. We're going to define and compute the distance between two vectors in Cn, the space of n-dimensional column vectors. And then we're going to determine if two vectors in Cn are orthogonal. So let's start with the definition of an inner product. If u and v are vectors in Cn, if they're column vectors, we define the inner product using this equation. So first of all, we have this notation here that we use to indicate the inner product of u and v. We put them inside these angle brackets with separated by a comma, and this is the formula that we use to compute the inner product of u and v. We're going to get a complex number, so this formula is going to give us a complex number, and the formula tells us to take the conjugate of component I for u and multiply it by component I for v, and then increment I from 1 to n. So we add up all these products from 1 to n, and that gives us a complex number, which is the inner product of u and v. We also call the inner product a scalar product sometimes to emphasize that it's a scalar and not a vector. So if you take two vectors and multiply them with this inner product, you get a scalar, not a vector. Here's a simple little example. I've got two vectors u and v here in C3, and you can see that the entries in each vector are complex. And if I want to compute the inner product of u and v, I first take the conjugate of u. So I'm going to take the conjugate of each entry in u and then multiply those entries by the corresponding entries in v. So I'll get the conjugate of 2 minus 3i, which is 2 plus 3i, multiplied by 5 plus 2i here, and then the conjugate of 3, well, 3 is real, so it is its own conjugate, times 1 minus 3i, and the conjugate of 1 plus I, which is 1 minus I, times 2. And then I do the arithmetic, combine the like terms, if you will. So the real parts get added together, 10 minus 6 plus 3 plus 2 to give me 9, and the imaginary parts get added together to give me 8i, and the inner product of u and v then is the complex number 9 plus 8i. Inner products satisfy these 6 properties. If I change the order of the inner product from the inner product of u with v to the inner product of v with u, then I need to take the conjugate. So the inner product of u with v is the conjugate of the inner product of v with u. There are a couple of distributive properties here. If I factor out a scalar, it depends whether the scalar is multiplying the first vector or the second vector, because of the definition of the inner product. If the scalar is multiplying the first vector, when it comes out, we take the conjugate of it. If it's multiplying the second vector, when we take it out, we don't take the conjugate of it. And then the last one says that if I take the inner product of a vector with itself, I'll always get a number that's greater than or equal to 0, and I will only get 0 if the vector itself is 0. Remember the if with two f's here is not a typo, it means if and only if. So the inner product is 0 if and only if the vector inside itself is 0. We define the norm of a vector using this notation. It looks like absolute value with 2 bars instead of 1. The norm of u is defined to be the square root of the inner product of u with itself. Our second theorem here tells us that the norm of a scalar multiple of a vector is the modulus of the scalar times the norm of the vector. So be careful about this notation here, the modulus of the vector. This is not the same thing as absolute value. Here's a quick review of the modulus of a complex number. If z is the complex number a plus bi, the modulus of z is defined to be the square root of the conjugate of z times itself. So if z is a plus bi, the conjugate is a minus bi, we multiply that by a plus bi, multiply everything out here, and we get the square root of a squared plus b squared. Remember that I squared is negative 1 because I is the square root of negative 1. So I squared is negative 1, so minus b squared times a negative 1 gives me plus b squared. Well, if we look at this formula, if I have a real number, if z is a real number and b is 0, then b squared here is 0, so the modulus is just the square root of a squared. This is actually the definition of absolute value in calculus, for example. So something just to keep in mind in your future math courses, particularly if you still have some calculus courses to go. Absolute value of a real number is really just the modulus. Okay, now let's look at the proof of this theorem. It's a simple direct proof just using the definitions of the norm and the inner product. So the norm of alpha times u by definition is the square root of the inner product of alpha u with itself. I can use the properties of inner products to factor out this alpha, which will come out as the conjugate of alpha, and then this one, which will come out as just alpha. Then I can use properties of square roots and split this product into the product of two roots. This one is defined to be the modulus of alpha, and the square root of the inner product of u with itself, well, that's just defined to be the norm, and so the theorem is proved. Another theorem tells us that the norm of a vector in Cn, so the entries in U may be complex, but the norm is a real number. And the proof, again, is just a real simple direct proof. The modulus of the norm is just equal to the norm. Sometimes we have complicated expressions where we'll end up with the modulus of the norm of some vector, and we can essentially just take off the modulus because the modulus of the norm is the norm, and again, we have a simple proof. We define the distance between two vectors in Cn to be the norm of the difference of the vectors. This is an important definition because very often we can't visualize Cn. In fact, C2 and above, we generally are not going to try to draw. So we can't really picture the distance between these two vectors, but no matter what the dimension is, in C3 or C300, the distance between two vectors is always defined to be the norm of the difference of the vectors. Another key definition is orthogonal. So we say two vectors are orthogonal if their inner product is 0. It's very straightforward. And if they are orthogonal, we will often write u and then this perpendicular symbol from geometry, which in linear algebra means orthogonal. So this is read u is orthogonal to v, and it means the inner product is 0. Okay, let's do another example. Let's say I'm given these vectors u and v. They're in C2, but since each vector has real entries, we can picture them here in R2. Like I said, we generally don't try to draw C2, but here is a picture of R2, and I can consider that u and v are just in R2. Here's u, here's v. We're asked to find the distance between u and v, and then also to decide if they're orthogonal. And it turns out that the distance between u and v is the length of this red line segment here, so I just drew that in for visual reference. But you don't have to know that in order to answer the question. In fact, we can start with the distance first. As we saw before, the definition of distance is the norm of the difference, u minus v. So here's u, here's v. We do the arithmetic, we get the difference, we take the norm using the definition, the square root of the inner product of the vector with itself. So we multiply minus 3 times minus 3 to get 9, plus 1 times 1, and we get the square root of 10. So the distance between u and v is the square root of 10. We do the inner product of u and v to decide if they are orthogonal or not. So 2 times 5 plus 3 times 2 gives us 16, which is not 0. So u and v are not orthogonal. If we look back at the picture, we can see that the angle between u and v does not look like it's 90 degrees. In R2 and in R3, if we measure the angle between two orthogonal vectors, we'll get pi over 2 radians, or 90 degrees. So if we're looking at a graph in R2, we can get a pretty good idea of whether vectors are orthogonal just by looking at the angle between them. If it looks like the angle is obviously not pi over 2 radians, then they're probably not orthogonal. If the vectors look like they might be at a 90-degree angle, then you can do the inner product to decide if they actually are orthogonal, because the inner product has to be exactly 0 for the vectors to be orthogonal. Okay, we'll finish up with a few more definitions and theorems that will be useful later. First, we'll define an orthogonal set. We'll say a set of vectors in Cn is orthogonal if the vectors in the set are pairwise orthogonal. Pairwise means that if I take any two vectors in the set and take their inner product, I'll get 0, as long as I is not equal to j, meaning I can't do u1 inner product with u1 or u5 inner product with u5. One of the properties of inner products tells us that I'll never get 0 unless u1 or u5 is 0 itself. So as long as I take inner products of distinct vectors, any two vectors in the set, I'll get 0. And if that happens, the set is said to be orthogonal. A handy theorem tells us that if I have a set of orthogonal vectors, the set is linearly independent. There's an important word in here, non-zero. An orthogonal set of vectors can contain the 0 vector. In fact, the 0 vector is orthogonal to every vector because the inner product of 0 with any vector is 0. But as we saw before, any set that contains a 0 vector is linearly dependent. So if I exclude the 0 vector, and in particular only consider orthogonal sets that don't have the 0 vector in them, then they are linearly independent. So we could think of this theorem as telling us that orthogonality implies linear independence. If the norm of a vector is 1, it's called a unit vector. Its length is 1. And if we have a vector that's not a unit vector, we can normalize it to create a unit vector. This theorem says if v is a vector in Cn, then if I multiply v by the reciprocal of its norm, then I'll get this vector, say u, and it will be a unit vector. In other words, the norm of u is 1, and the proof, again, is just a direct proof using the definitions. So the norm of u, well, substitute this for u. Notice that 1 over the norm of v is going to be a complex number, so we could think of this as alpha. And we saw before that the norm of alpha times v is the modulus of alpha times the norm of v. Well, the modulus of a ratio is the ratio of the moduli, which is plural for modulus. So we have the modulus of 1. Well, remember, if a number is real, the modulus is the same as the absolute value. So the modulus of 1 is 1. And as we saw before, the modulus of a norm is just the norm. And then I've got 1 over the norm of v times the norm of v. So the norm of v divided by itself, you could think of it that way. That's just 1. And then finally we say, if I have an orthogonal set, so a set of vectors that are pairwise orthogonal, if they're all unit vectors, then it's called an orthonormal set. And we'll see later that these types of sets, orthonormal sets, have some really nice properties. Okay, now you should be able to compute inner products, compute distance between vectors, and use inner products to decide if two vectors are orthogonal.